Hi, my name is Kate, and this is Lab 5 Physics 2211, where I chose to look at the Slinky drop. For this lab, we were allowed to choose our own adventure, so I decided to analyze the following Slinky. This model shows the motion of a stretched Slinky dropped from static equilibrium. To analyze its motion, I looked at the forces acting on it and explained why those forces caused the motion we will see on the next slide. This is very similar to Lab 2, motion of a falling object. Alright, so there's the video used for analysis. As we can see, the bottom of the Slinky remains in the same position as the top of the Slinky falls. Once the Slinky is compact, it falls like a point particle until it hits the ground. The motion is unique because based on our physics principles, we would assume that the bottom of the Slinky would fall as soon as he lets go of the top, but that didn't happen, so let's discover why. So the two outside forces acting on our system, which is the Slinky, are the force of gravity and the drag force. These two forces act in opposing directions, so the magnitudes will be subtracted when solving for the net force. The tension force from the top of the Slinky on the bottom of the Slinky is only in effect when the two ends are not together. So this force goes away when the Slinky comes together, acting as one solid object. Newton's second law is going to be the main physics principle seen here. From this, we can use several different formulas, such as the velocity update formula and position update formula. These will allow us to make estimates as to where an object should end up and how it should act. These formulas will be used in our computational model to compare the predicted model to the actual motion as seen in the video. As you can see, I wrote two different net force equations. This is because the types of forces actually change as the Slinky falls. When only the top is in motion, drag force can be considered negligible, and it should be noted that we are analyzing the bottom of the Slinky. When the Slinky comes together, we treat the system as a solid object falling because gravity is pulling it closer to the Earth, but the drag force from the air pushes slightly up on the object, slowing it down a little bit. Alright, I put the video in Tracker and set my axis to be the bottom of the Slinky. I then calibrated Tracker to focus on the bottom of the Slinky, and it tracked its motion to form the two graphs as seen on the right. The X position remains unchanged, but the Y position of the bottom changes as soon as the top hits it. The actual mass of the Slinky was unknown, so I made it 1 kilogram. The bottom of the Slinky starts as the axis, so its initial position is 0, 0, 0. It also starts at rest, so its initial velocity is also 0, 0, 0. Through a process of guess and check, I found the drag coefficient to equal 60, which is B. This calculation loop shows the system's motion as only the top of the Slinky is falling. The bottom of the Slinky remains stationary because the total net forces acting on it are equal to 0. The force of gravity pulls down on the bottom, but the force of tension from the top of the Slinky counteracts it because it pulls up. The next calculation loop tracks the motion of the Slinky as the two ends are together. The force of gravity is greater than the drag force, so the Slinky falls straight down. The computational model provides the graph on the right. Again, this is a model for the bottom of the Slinky, so it remains stationary as seen in the video until the top hits it. The negative linear line shows the Slinky falling. It is so steep because drag doesn't play a huge role. If the Slinky was way lighter, then drag would have a bigger impact. The magenta arrow represents gravity and the cyan arrow shows drag. Before the cyan arrow, there was a yellow arrow showing tension. The experimental and predicted graphs are nearly identical, but some source of air could have been the drag coefficient. I did a process of plugging and chugging, so a more accurate D value could have been present. Another source of air could have been the video itself. I uploaded the video off of YouTube, so I didn't have any of the actual measurements, such as mass or position. As discovered from this lab, a Slinky doesn't act as a normal object when falling from stretched static equilibrium because of the tension force it experiences. This tension force is the reason the bottom of the Slinky remains stationary after the top is dropping, making it look like it is defying gravity. In reality, the tension force is balancing out the gravity force until the two ends meet. Thank you.